Picture this, it's mid-1943, and the Panther tank, officially named the Panzerkampfwagen 5 Panther, PZKPFW5, rumbles onto the battlefields of World War II. This German medium tank, designed to counter the Soviet T-34, begins its journey on both the Eastern and Western fronts. In February 1944, a significant change occurs. Hitler decides to simplify the name, dropping the Roman numeral 5, and the tank is now just the PZKPFW Panther. English reports sometimes call it the Mark V, but the Panther's reputation is growing beyond names. Initially, the Panther was meant to replace older tanks like the Panzer III and Panzer IV. However, it ends up fighting alongside the Panzer IV and the heavier Tiger I until the war's bitter end. The Panther shares the same powerful 690 horsepower Maybach V12 engine as the Tiger I, but it's lighter, faster, and handles rough terrain with ease. This agility comes at a price, though. Its side armor is weaker, making it vulnerable to side attacks, and its high explosive shells aren't as effective. Yet, in the open fields and during long-range engagements, the Panther excels. With excellent firepower, protection, and mobility, the Panther's only drawback is its reliability. The Panther is cheaper to produce than the Tiger I. To speed up production and cope with material shortages, key design elements like the armor, transmission, and final drive are simplified. Despite these efforts, some critics label the Panther as over-engineered. The Panther's combat debut at the Battle of Kursk in the summer of 1943 is a rough start. Rushed into battle, it suffers significant losses due to mechanical issues. By late 1943 and early 1944, most of these problems are fixed. However, challenges like bombed production facilities, shortages of high-quality materials and fuel, limited training space, and declining crew quality still impact the tank's performance. Weighing around 44 tons, the Panther is close in weight to heavy tanks of other nations. This weight sometimes causes logistical issues, like trouble crossing certain bridges, but its high power-to-weight ratio keeps it highly mobile. Interestingly, the Panther's production variants don't follow the usual alphabetical order of German tanks. The first model is the Panther D, Ausf. D, followed by the A and G variants. This unique naming adds another layer to the Panther's storied history on the battlefields of World War II. Development and production. In June 1943, Albert Speer stood beside a T-34 Model 1940, contemplating the tank that had changed the course of armored warfare. The Panther tank, born from a project initiated in 1938, was designed to replace the Panzer III and Panzer IV. The VK-20 series, initially aimed at creating a 20-ton fully tracked vehicle, evolved as encounters with the formidable Soviet T-34 and KV-1 tanks reshaped German needs. This led to a requirement for a 30-ton tank, a direct reaction to the Soviet challenge. General Heinz Guderian, recognizing the T-34's superiority, formed a special commission to study the Soviet tank. They noted its sloping armor, which deflected shots and increased effective thickness, its wide tracks for better mobility on soft ground, and its powerful 76.2mm gun. With these insights, Daimler-Benz, DB, and Maschinenfabrik Augsburg-Nürnberg AG, MAN, were tasked with designing a new tank, the VK-30.02, by April 1942. DB's design, the VK-30.02 mimicked the T-34 with a hull and turret placed forward and powered by a diesel engine, enhancing operational range and reducing flammability. Despite Hitler's preference for a diesel engine, WWII 6 favored the torsion bar suspension used by MAN, arguing it allowed for a wider hull and greater internal space. MAN's proposal featured a more conventional layout with a drive sprocket at the front, a centrally mounted turret, and a petrol engine. The design included 8 torsion bar suspension axles per side, drawing inspiration from the Tiger I's overlapping road wheels, which distributed ground pressure evenly. MAN's design also utilized an existing Rheinmetall turret, expediting production. From January to March 1942, both designs underwent rigorous review. Despite initial favor towards DB's proposal, a leak revealed critical insights, leading to MAN refining its design. On March 5, 1942, Albert Speer informed Hitler that the DB design was considered superior. However, a special commission's review in May 1942 ultimately selected MAN's design, primarily because it used an existing turret, saving crucial development time. Albert Speer, reflecting in his autobiography Inside the Third Reich, described the Panther's evolution. Initially intended as a nimble 30-ton tank with the same engine as the Tiger, Hitler's insistence on additional armor and larger guns pushed the Panther's weight to 48 tons, nearing the Tiger's original weight. In September 1942, a prototype of the MAN Panther was ready. After rigorous testing at Kummersdorf, It was approved for production. However, the actual start was delayed due to a shortage of specialized machine tools needed for the hull's machining. By December, finished tanks started rolling out, although they faced reliability issues. The demand for the Panther was so high that production soon extended beyond MAN to include Daimler-Benz, Maschinenfabrik Niedersachsen Hanover, MNH, and Henschel and Zone. Initially, the target was set at 250 tanks per month at the MAN plant in Nuremberg. This goal increased to 600 per month in January 1943. Despite concerted efforts, this figure was never achieved due to Allied bombing disruptions, as well as manufacturing and resource bottlenecks. Production in 1943 averaged 148 tanks per month. By 1944, production ramped up to an average of 315 per month, with a peak of 380 in July. By the war's end in March 1945, at least 6,000 Panthers had been produced. Frontline combat strength peaked on September 1, 1944, with 2,304 tanks, but a record number of 692 tanks were lost that same month. In terms of labor hours, it took roughly 1.25 times the effort to build a Panther compared to a Panzer III. The cost, without weaponry, for a PZ KPFW-3 was Rm 96,163, while a Panther cost Rm 117,100. Allied forces targeted critical production points, such as the Maybach engine plant, which was bombed on the night of 27/April 28, 1944, halting production for 5 months. A second factory, the Auto Union Ziegmar plant, began operations in May 1944. Bombing raids also targeted Panther factories, starting with the Daimler-Benz plant on August 6, 1944. The MAN plant faced multiple attacks, including on 10 September, 3 October, and October 19, 1944, as well as in January and February 1945. MNH was bombed in March 1945. These bombings not only disrupted production but also caused a steep decline in spare parts production. Spare parts, which made up 25 to 30% of tank production in 1943, dropped to just 8% by late 1944. This exacerbated reliability issues and forced field units to cannibalize tanks for parts. The Panther tank cost 117,100 Reichsmark, RM, to produce. For comparison, the Stug 3 cost 82,500 RM, the Panzer III cost 96,163 RM, the Panzer IV cost 103,462 RM, and the Tiger I was the most expensive at 250,800 RM. These costs did not include the armament and radio. The use of slave labor in production lines significantly reduced costs but also increased the risk of sabotage. A 1947 French Army study revealed that many Panthers had been sabotaged during production. To cope with the rising demand, the Germans focused on methods that would allow higher production rates and lower costs. For instance, the total cost of the early production Tiger I in 1942 to 1943 was reported to be as high as 800,000 RM. Streamlining production of German armored fighting vehicles began after Albert Speer became Reichsminister in early 1942 and continued to accelerate through to 1944. The Panther tank's production coincided with this period of increased manufacturing efficiency. At the start of the war, German manufacturers used labor-intensive and costly methods unsuitable for mass production. Even with improvements, German manufacturing efficiency never reached the levels achieved by the Allies during World War II. Design characteristics. The weight of the Panther tank increased from the planned 35 tons to 45 tons in the production model. Hitler was thoroughly briefed on the MAN and DB designs in a report by Guderian's Tank Commission. While the armor protection was initially deemed inadequate, the rear-mounted motor design was favored. The decisive factor for Hitler was the quick transition into production. On May 15, 1942, Oberst Fichtner informed MAN that Hitler had chosen the MAN Panther for series production. The upper glacis plate was increased from 60 mm, 2.4 in, to 80 mm, 3.1 in. Hitler also requested an attempt to increase it to 100 mm, 3.9 in, and demanded that all vertical surfaces be 100 mm, 3.9 in. The turret front plate was increased from 80 mm, 3.1 in, to 100 mm, 3.9 in. The Panther was rushed into combat before all its initial problems were resolved. Over time, reliability improved significantly, making the Panther a very effective fighting vehicle, though some design flaws, such as weak final drive units, persisted. The Panther's crew consisted of 5 members: the driver, the radio operator, who also manned the bow machine gun, the gunner, the loader, and the commander. The Panther initially rolled out with a Maybach HL 210P30 V12 petrol engine, delivering 650 horsepower at 3,000 revolutions per minute. These early engines used 3 simple air filters. Starting in May 1943, Panther switched to the Maybach HL230P30 V12 engine, which provided 690 horsepower at 3,000 revolutions per minute. To save on materials, this engine used a cast iron block instead of the light alloy block found in the HL210. It also featured 2 multi-stage cyclone air filters to better handle dust. However, low-grade petrol reduced the engine's power output. The Panther had a fuel capacity of 190 gallons, giving it a range of 160 miles on roads and 62 miles off-road. The HL230P30 engine was designed with a compact tunnel crankcase, minimizing the space between the cylinder walls. The crankshaft had 7 discs with roller bearings and crankshaft pins between each disc. The V12's design required fork and blade connecting rods for each cylinder pair, which initially caused significant problems. Early models suffered from blown head gaskets until improved seals were introduced in September 1943. In November 1943, better bearings and an engine governor that reduced the maximum speed to 2,500 revolutions per minute were added. An 8th crankshaft bearing was included from January 1944 to further reduce engine failures. The Panther's engine compartment was designed to be watertight for fording water obstacles, but this led to poor ventilation and overheating. Early fuel connectors were not insulated, causing fuel fumes to leak into the engine compartment and result in fires. Additional ventilation helped, but did not completely solve the problem. Other measures to reduce engine fires included improved coolant circulation and reinforcing the fuel pump's membrane spring. Despite these issues, the fighting compartment remained safe due to a solid firewall separating it from the engine compartment. Engine reliability improved over time, with an average service life of about 1,200 miles or around 100 working hours without needing to dismount the engine. However, a French assessment in 1947 of captured Panthers from Normandy concluded that the engines averaged a lifespan of 620 miles and a maximum of 930 miles. The Panther's suspension system was a key component of its design, featuring front drive sprockets, rear idlers, and 8 double interleaved rubber-rimmed steel road wheels on each side. This setup, known as the Skate-to-Loafwork design, was supported by a dual torsion bar suspension. Developed by Professor Ernst Lehr, this dual torsion bar system provided the Panther with a wide travel stroke and allowed for rapid oscillations, resulting in high reliability and relatively high-speed travel over uneven terrain. The necessity for the bars to run across the length of the hull below the turret basket increased the overall height of the tank. When damaged by mines, removing the torsion bars often required a welding torch. While the Panther's suspension was considered over-engineered, its interleaved road wheel system made replacing inner road wheels a time-consuming process, although the tank could still operate with missing or broken wheels. The interleaved wheels often became clogged with mud, rocks, and ice, especially in the harsh winter weather following the autumn mud season on the Eastern Front. Although the tank's design minimized the problem of the running gear getting blocked by mud or snow, shell damage could cause the road wheels to jam together, making them difficult to separate. The interleaved wheels, standard on all German half-tracks, provided better flotation and stability, as well as additional armor protection for the thin hull sides. However, the complexity of this design meant no other country adopted it for their tanks. In May 1944, the Inspector General of Armored Troops reported on the Panther's tracks and suspension. After a mileage of between 1,500 km and 1,800 km, the tracks show significant wear. In many cases, the guide horns of the tracks bend outward or break. In some instances, the tracks had to be replaced when a series of reinforcement guide horns were broken. The guide horns are probably too weak as they bend easily. Due to constant operations and a shortage of spare parts, the bearing system has not been maintained or repaired as it should be. Consequently, the bearing system in the available tanks is in very poor condition and has sometimes caused track or suspension failures. In September 1944, and again in March and April 1945, MAN produced a limited number of Panthers with overlapping, non-interleaved steel-rimmed road wheels, originally designed for Henschel's Tiger II and late series Tiger I tanks. These steel-rimmed road wheels were introduced from chassis number 121052 due to raw material shortages. From November 1944 through February 1945, a conversion process began to use sleeve bearings in the Panther tank because of a shortage of ball bearings. The sleeve bearings were primarily used in the running gear. Plans were also made to convert the transmission to sleeve bearings, but these were not carried out due to the end of Panther production. The Panther tank steering system was designed for precision. It featured a 7-speed AK7-200 Synchromesh gearbox from Zonrad Fabrik Friedrichshafen, ZF, and a MAN single radius steering system. Operated by steering levers, each gear had a fixed turning radius, ranging from 16 feet in first gear to 260 feet in seventh gear. This required the driver to anticipate turns and shift gears accordingly. For sharper turns, the driver could engage the brakes on one side. This was a simpler design compared to the Tiger tanks. The AK-7-200 transmission allowed for pivot turns, but only when the ground resistance on both tracks was the same. This maneuver often caused high torque, leading to final drive failures. The transmission system was prone to premature stripping of the third gear, worsened by alloy shortages which made the gears brittle and more likely to fail. To repair the final drive, the entire driver's compartment and transmission had to be disassembled and lifted out. One of the Panther's main weaknesses was its final drive unit. Originally, MAN had designed the Panther with an epicyclic gearing system similar to the Tiger I. However, due to a shortage of gear cutting tools, numerous design simplifications were made for mass production. Despite objections from designers and Army officers, the final drive was changed to a double-spur system. Although simpler to produce, the double-spur gears had higher loads, making them more prone to failure. Dr. Puschel of MAN highlighted the primary cause of the Panther's final drive failures. According to his report, the failures were mainly due to the fatigue of the compound intermediate gear, caused by the low core strength of the material and the lack of case hardening in critical areas. Additionally, the use of split-ring dowels with only a few bolts to secure the main drive gear to its flange proved inadequate. This issue was eventually resolved by fitting additional bolts. In September and October of 1944, German industry made several modifications to the final drive units on the Panther Ausf. To enhance their durability. Jacques Littlefield, from the Military Vehicle Technology Foundation, which restored a Panther Ausf. Mentioned that they found the alloy and gears used in the final drive construction to be of high quality, comparable to modern standards. He speculated that the main problem with the final drive was its design for a much lighter version of the Panther. As the tank's armor was increased, there was no room to strengthen the final drives to handle the additional weight. Armor. In the early stages of its production, the Panther tank was equipped with a face-hardened glassy plate, but by March 1943, this was replaced with a homogeneous steel glassy plate. This change came as Armies adopted armor-piercing capped rounds, which negated the benefits of face-hardened armor. By August 1943, all Panthers featured the homogeneous steel glassy plate. The Panther's front hull boasted 3.1 inches of armor angled at 55 degrees, welded and interlocked with the side and bottom plates for added strength. This combination of armor thickness and sloping made it resilient against most Allied weapons. However, heavy artillery, such as the Soviet 122mm A-19 and the American 90mm M3, could penetrate the upper glacis at standard combat ranges. The side armor of the Panther was much thinner, measuring between 1.6 to 2.0 inches. This reduction in thickness was necessary to keep the tank's weight manageable but left it vulnerable to side hits from Allied anti-tank guns. To address this, German tactics emphasized flank protection, and engineers designed the Panther II to overcome this weakness. Although this new model was nearly complete, it was ultimately abandoned. To improve side protection, 0.20-inch thick spaced armor skirts, known as Schürzen, were added to shield the lower hull from anti-tank rifles like the Soviet PTRS-41. From September 1943, a Zimmerit coating was applied to late Ausf models to protect against magnetic mines. Older Panthers received this coating in the field following an order in November 1943. However, by September 1944, the application of Zimmerit was halted due to rumors that it caused vehicle fires. Panther crews were aware of their tank's vulnerabilities and often hung spare track links or road wheels on the turret and hull sides for extra protection. The rear hull top armor, only 0.63 inches thick, had radiator fans and air intake louvers over the engine compartment, making it susceptible to aircraft strafing. As the war dragged on, Germany faced shortages of critical alloying metals like nickel, tungsten, and molybdenum, essential for armor plate production. The loss of these metals, due to events like the bombing of the Knaben mine in Norway, forced Germany to use substitutes, resulting in brittle armor plates that fractured under fire. Tests by U.S. Army officers in August 1944 in Isigny, France revealed catastrophic cracking in the armor of 2 out of 3 Panthers examined. Armament. The Panther tank came equipped with a powerful Rheinmetall Borsig 7.5 cm KWK-42 L/70 main gun, which had a semi-automatic shell ejection system. Early models carried 79 rounds of ammunition, while the Ausf. G variant could hold 82 rounds. The gun fired 3 types of shells: UPC-He, PZGR, 3942, He, SPRGR, 42, and APCR, PZGR. 40-42. However, the APCR rounds were often in short supply. Despite being a common caliber, the Panther's gun was one of the most formidable during World War II due to its high muzzle velocity and excellent armor-piercing capabilities. In comparison, Allied tank guns of similar caliber didn't match the Panther's muzzle energy. The British Sherman Firefly's 17-pounder gun was an exception, with its APDS rounds offering more penetration power, but it was less accurate due to the separation of shot and sabot. The Panther's flat trajectory and high accuracy made hitting targets easier, especially moving ones. Its 75mm gun had greater penetrating power than the Tiger I's 88mm gun, although the Tiger's larger shell caused more internal damage if it penetrated. The Panther's 75mm He round was less effective than the Tiger's 88mm He round for infantry support but comparable to other 75mm He rounds used by different tanks and assault guns. The Panther also featured two MG-34 machine guns. One was mounted coaxially with the main gun, and the other was positioned on the glassy plate, operated by the radio operator. Early models, the Ausf. D and early Ausf. A, had a letterbox flap for the whole machine gun. Later models, including Ausf. A and all Ausf. G, used a ball mount with a K.Z.F.2 sight for the whole machine gun. Initially, the Ausf. D came with the Nebelwurfgerät smoke launcher. Later models, Ausf. A and Ausf. G, were equipped with the Nahverteidigungswaffe close defense weapon. Turret. The front of the Panther's turret had a 100mm, 3.9 inches, thick curved cast armor mantlet. This curved design helped deflect incoming shells, but it also created a shot trap. If a shell hit the lower section and deflected downwards, it could pierce the thin forward hull roof armor, potentially causing severe damage inside the tank. The compartment housed both the driver and the radio operator, sitting on either side of the gearbox and steering unit. Additionally, 4 magazines containing main gun ammunition were located between the driver and radio operator seats and the turret, directly under the gun mantlet when the turret faced forward. From September 1944, Panther Ausf. G models started featuring a redesigned mantlet with a flattened, thicker lower chin to prevent such deflections. However, the conversion to the chin design was gradual, and many Panthers continued to be produced with the rounded gun mantlet until the end of the war. The Ausf. A model introduced a new cast armor commander's cupola, which replaced the older forged cupola. This new cupola had a steel hoop to mount a third MG-34 machine gun for anti-aircraft use, in addition to the coaxial and bow machine guns. The Panther's turret had a powered traverse system provided by the variable-speed Boehringer Sturm L4 hydraulic motor. This motor was driven by a secondary drive shaft from the main engine, similar to the system used on the Tiger tank. Early production Panthers had a maximum turret traverse speed of 6 degrees per second. Later versions added a high-speed traverse gear, allowing the turret to rotate 360 degrees at up to 6 degrees per second in low gear, independent of engine RPM, or up to 19 degrees per second with the engine at 2000 RPM. At the maximum engine speed of 3000 RPM, the turret could traverse at over 36 degrees per second. The gunner controlled the direction and speed of traverse using foot pedals. This system allowed for precise control, with a light touch resulting in a minimum traverse speed of 0.1 degrees per second. Unlike most tanks of the time, this system enabled fine aiming without the gunner needing to use a handwheel. Ammunition storage. One of the Panther's main weaknesses was its ammunition storage. The ammunition for the main gun was stored entirely within the hull, with a large portion kept in the side sponsons. In the Ausf D and A models, 18 rounds were stored on each side next to the turret, totaling 36 rounds. For the Ausf G model, which had deeper sponsons, 24 rounds were stored on each side of the turret, increasing the total to 48 rounds. Additionally, all models stored 4 rounds in the left sponson between the driver and the turret. Inside the hull of the Ausf D and A models, an additional 36 rounds were stored, with 27 rounds in the forward hull compartment directly beneath the mantlet. The Ausf G model reduced hull storage to 27 rounds, with 18 rounds in the forward compartment. All models also kept 3 rounds under the turret's turntable. The Panther's design made the side sponsons, where 52 rounds were stored, particularly vulnerable. Penetration in this area often led to catastrophic ammunition fires, making it a critical weak point. The loader, positioned on the right side of the turret, accessed the right sponson and hull ammunition bins, making these his primary sources of ready ammunition when the turret was facing forward. Crew. The Panther tank operated with a crew of 5, the commander, gunner, loader, driver, and radio operator. The crew members were strategically placed within the vehicle to maximize efficiency and effectiveness. The commander, loader, and gunner were stationed in the turret. The commander was responsible for overseeing the tank's operations and making critical decisions during combat. The loader's task was to ensure that the main gun was always ready to fire, swiftly loading shells into the breech. The gunner aimed and fired the main gun, working closely with the commander to target enemy positions. In the hull of the tank, the driver and the radio operator had their designated positions. The driver sat at the front left side, managing the tank's movement and ensuring it navigated the battlefield effectively. Next to him was the radio operator, who also handled the tank's bow machine gun. The radio operator's dual role was crucial, as maintaining communication with other units and providing additional firepower were both vital for the tank's success. This division of roles allowed the Panther crew to operate with precision and coordination, each member fulfilling a specific function to keep the tank combat ready and responsive in the heat of battle. Combat history and use. Panther deployment and early issues. The Panther tanks were first sent to form Panzerabteilung 51 on January 9 and Panzerabteilung 52 on February 6, 1943. These early Panthers faced significant mechanical issues. The engine had a tendency to overheat, and problems with connecting rods and bearings were common. Fuel leaks from the pump or carburetor, along with oil leaks from gaskets, led to engine compartment fires, resulting in 3 Panthers being completely written off. Transmission and final drive failures were frequent and challenging to repair. To address these issues, all Panthers were recalled to Falkensee and Nuremberg from April to May 1943 for major overhauls. However, not all problems were resolved, necessitating a second round of repairs at Grafenwohr and Erlangen in June 1943. Improvements came with the Ausf A and later the Ausf G models, leading to increased reliability. By the end of 1943, the average operational rate for Panthers had risen to 37%. This improved further to 54% in 1944. By mid-1944, the Panther reached its peak performance and was considered the most formidable tank on the battlefield. German General Hasso von Manteuffel praised the Panther as Germany's most satisfactory tank, noting that it would have been nearly perfect with a lower silhouette. The Panther tank, despite its early mechanical challenges, evolved into one of the most respected and formidable tanks of World War II. Its blend of firepower, armor, and mobility set new standards for tank design. The improvements made over time transformed it into a highly effective weapon on the battlefield, earning it a legendary status among military vehicles. As we reflect on its storied history, the Panther stands as a testament to the relentless pursuit of engineering excellence and the enduring spirit of innovation in the face of adversity.